Blender 4.2 has been released, and I want to take the opportunity to go over some of the things that are new for geometry nodes. In this video, we'll take a look at the new matrix socket. There is also another video about what is new for node tools that you can check out afterwards. If you go to the release notes page on blender.org and you scroll down to the geometry nodes section, you find that there is a whole new socket type in geometry nodes for matrices now. This little demo file here shows how this new socket can be used to handle transformations much more easily than was possible before. In this case, to make a little stacking modifier for this pile of pizza boxes. Let me first give you a quick introduction to what the purpose of this new socket type is, and then walk you through the creation of the modifier in this demo in a little bit more detail. So, what even is the point of a matrix? Well, there's a lot of mathematical background that can be covered when talking about matrices, but that's not really important right now. The most important thing to understand for using the matrix socket in Blender's geometry nodes is that a 4x4 matrix is a very useful way to represent a transformation. That is also what Blender does under the hood. A transformation in general is made up of the three components for translating, rotating, and scaling. So instead of thinking about a matrix as a grid or 4x4, which doesn't really help you to understand what exactly is going on, you can just think of it in the context of transformations of translation, rotation, and scale. So for that, the easiest way to create a matrix in Blender's geometry nodes now is to use the Combine Transform node. There you simply get the option to plug in your values for translation, rotation, and scale, and out comes the matrix. But you can also retrieve your transformation directly from, let's say, an object. So here on the modifier of this cube, for example, let's drag and drop the camera object into the node tree, and there you can see that besides the object transformations for location, rotation, and scale, we also get the transform matrix as one socket. This one transform socket now encapsulates all the transform information from these three individual sockets. And that can make it a lot easier to handle in the node tree. For example, if we now want to move the cube into the same transformation as the camera, we can very easily do that using the transform geometry node and then setting it to the matrix mode. And then connecting the transform of the camera to the transform of the operation puts the cube directly into the exact same position, rotation, and scale as the camera. So if you move that around now, you can see how it's really constrained to the camera directly, all using geometry nodes. This would have been possible before using the location, rotation, and scale, but it would have been a little bit more tedious. And with this transform now, we can also do some additional things. Like, for example, we can combine it with another transform. So let's use the Combine Transform node. And then to do both of these transformations at once, we can use a Multiply Matrices node. Again, I'm not going to go into the mathematical detail of why this works, but multiplying two matrices basically just means combining both of the transformations in this context. So if I plug both the matrices in here and then add some value in the translation, you can see how that also moves the cube on top of the transformation we did into the camera. But here you can see that the translation vector that we plug in for a positive x value doesn't actually move the cube along the x-axis of the object. And this is where the order of these two inputs comes into play. Since we have the transformation of the camera first, this means that this transformation happens in the space of the camera. So we're currently moving the cube along the x-axis of the camera. If I reverse the order of these two inputs, you can see how now this vector has an effect on the x-axis of the cube object. So this is something to be wary of when you're combining matrices for transformations. Another thing you can do, for example, to change the transformation around is to invert the matrix. For transformation, this also does exactly what you would think it does. It inverts the transformation by doing the exact opposite. These kinds of transformations between different spaces, from global to local and between different objects, etc., can get quite complicated quite quickly. So it's very nice to just combine the whole concept of the transformation in a single socket with simple applications rather than having to handle them individually as location, rotation, and scale. Another aspect of this matrix socket is that it doesn't simply just work for a single matrix that is carried from these links. Since it is a whole new socket type, it can also be applied to fields and attributes. So you can store a whole transformation matrix for each element of your geometry, for example, for each point of the mesh. This will come in handy in just a second when we go over the demo file. Alright, so let's get to stacking some pizza boxes. If you download the demo file from the release notes page, you can see that there's a relatively simple scene with this guy carrying pizza boxes on a Vespa. And there's just one modifier on the pizza stack that has some controls for you to control the height of the stack, and then some additional settings for randomization. And this is heavily relying on the use of matrices to propagate the transformations between these different boxes. So one thing, for example, is that as I increase this random rotation or the random offset, the pizza boxes don't just simply move individually. They all affect each other. So just like on a real stack of pizza boxes, if I just draw a really crude example here, the orientation of the lower box will affect the ones above it. So if there's a box with a slight tilt to it, the ones atop it will have the tilt as well. That was previously not that simple to do, but now with the matrix node, it's pretty easy to get the transformation of one element to affect the other ones above it. So let's go over how that works. Another aspect of this example case is that you can see clearly when I crank up the number very high, there is a slight bounce that goes through the pizza stack as the Vespa is jittering. And this is actually going from the bottom all the way to the top. For that, it's also using the matrix socket in a very simple simulation setup. And of course, this can break the laws of physics to create this very fun looking effect. So then let's get to stacking those boxes. First off, we'll start with a brand new cube that I'll go into edit mode on and then scale it to 0.5 size, because that means that each edge is exactly 1 unit. And then move it up on the z-axis by 0.5, which means that it's standing nicely on its origin point. That will be useful for the node setup. So let's start by creating a new geometry nodes modifier. Let's call that one pizza stack. And then now let's start by setting up the base for this stack. What I want to start with is a whole bunch of instances of this cube, which are going to be my pizza boxes. For that, I'm going to start out with a points node to give me a bunch of base points. Set that to 25 for now. And then an instance on points node. And what we'll instance as the geometry is going to be my input from the cube. And as you can see in the spreadsheet editor, now we end up with 25 instances of that same cube. So let's squish them a little bit more into pizza box shape by using a random value node and then tweaking the settings. So let's start with 1 on the XY axis, but go a little bit higher to have some more randomness to 1.5. And then on the Z axis, I want only low values. So let's go from 0.05 to 0.3. And then we get a nice variation of shapes. Now, all of these different instances have their exact size as the scale. And that is something that we can simply use with the instance scale node. So this is where we get the information of the height of each of these cubes. And that is something that we'll need to create the stack. To get a better view of what we're looking at, let me just go into local view on this object. So how do we now get these boxes into the right place? The main node that we'll use to orient these instances is the set instance transform node. This one lets us directly set the exact transformations for all of these boxes using the new matrix socket. So if I now add a combine transform node, you can see that all of the scale that we've been randomizing before is now set back to exactly what is defined in this node. So let's combine the instance scale in there to make sure that we keep that around. And then the translation and rotation, we can just set to any other value, and those will be applied to all the instances. Now we just need to figure out where they actually should be for each instance. For that, I'm going to show you a little trick that is very useful. Let's use the accumulate field node. So what this node does is that for a domain of the geometry, in our case that is going to be the instance domain, it goes through all the different elements within the same group and then accumulates the values of a certain field. In our case, that is going to be a transform field. So let's set the data type to transform. And then what that does is that this node will go through all the individual instances for these cubes and then accumulate the transforms. So instead of each cube just knowing its own transformation, this will go through all of the previous ones and add them on top of each other, which is exactly what we need for this stack. Let me show you how that works. Let's connect the trailing output of this node to a separate transform node. And for this, we only want the translation and the rotation, so we plug that into our combine node, because the scale is already taken care of. Right now, the input for this accumulate field node is nothing, so we're not applying any transformation at all for each of these instances. But now, as I use another combine transform node to give me a matrix field, and I tweak these values, you can see how each of these cubes is moved a little bit more than all the previous ones combined, rather than just moving them all at once. And that is the same also for the rotation and the scale. So there you can see that it's very useful to just use the concept of a transform and the accumulation rather than having to do all the math yourself. So all the previous pizza boxes are influencing the ones on top. So now let me just zero this out again. And then we can actually use the exact information that we have over the size of all these cubes for the translation offset of them. We only need the Z component, so let's use a multiply node and multiply it with the 0, 0, 1 to cancel out the X and the Y component. And as we connect this, you can already see how this works perfectly. So what is happening right now is that each cube is being offset by the accumulation of all of the sizes of the cubes that came before it. So this cube is set exactly to the combination of the height of the two before it, and then the next cube is set on top of the three before it, and so on. And if I change the bounds of the random scale, you can really see how this works perfectly, even if I have very different heights for all of these cubes. And this is already a very useful little stacking setup that you can use in a more generic way for other applications as well, with just a few nodes. So now let's give this stack a bit more variation. Let's frame this as our main stacking part of the modifier, and then also add some variation to the rotation. For that, let's simply just connect this to a random value node, and you can already see how it is crumbling up on itself. Let's put the range from -1 to 1 to get it centered around 0, and then scale the vector by a value. So now we have fine control over the strength of this effect. And here you can see this is basically what we had in the final setup to control some variation in how the stack is leaning. and if I change the random seed, it changes the overall shape. And again, this is quite different from what it would look like if we just rotated all the pizza boxes on their own, since they really have an effect on each other. So let's do the same thing to introduce a slight offset to the translation. I'll just add another add node, and then use yet another random value node. But we don't want any offset in the z direction, so let's set that to 0. And then we want it centered around 0, so let's put the minimum bounds to -1. And then also add another scale node to control the strength of that effect. Now we can just very easily expose these as controllable parameters in the modifier by typing in input and creating a new group input. Just make sure to name them accordingly so you don't forget what they actually mean. Let's also expose the number of cartons. And there you go, that's a big chunk of the setup already done. We can dynamically control the amount and the random offset, giving us a very wild stack of pizza boxes. So next up, let's create the bounce effect that goes through the whole stack as the Vespa's jittering. The idea for that is quite simple. This setup already has a control empty that bounces around with the movement of the vehicle. And then this is what we're going to use to move the bottommost pizza box. We're basically going to just constrain it exactly to that. And then we're going to create a simulation to get the offset from that transformation and move it along through the stack. So there's going to be a little bit of delay to move all of the additional pizza boxes on top by that transformation. And each frame it's going to move a little bit further through the stack, and that way go all the way to the top. So let's start with that setup by making a bit more space and then adding in the simulation zone. To get familiar with how the simulation zone works in general, there is also another video on the Blender YouTube channel if you want to check that out. Here I'm not going to go into full detail explaining that. But essentially how it works is that we get some geometry in on the very first frame of the simulation, and then for each frame afterwards there is a simulation loop happening between the output node and the input node, where everything we pass out on one frame is passed back in on the next one. In this case, the data that we want to simulate over is going to be exactly a new matrix attribute. So with this simulation selected, let's go to the Properties panel, and then in the Node panel, add a new entry for simulation data. Let's call this the transform, and then change the socket type to matrix. Here we also need to keep in mind that the geometry that we're working with is made up from instances and not meshes. So the attribute domain needs to be changed to instance as well. Let's make a very little test setup to see how this works. So let's add another set instance transform node and then connect that transform attribute, as well as a viewer node with Control-Shift-Click. And right now it just resets all of the transforms to 1. But if we connect this to complete the loop, and then also do a multiplication with another transform matrix, and then type in some value, we can see how now this actually changes the transformation of the cubes over time. So with each frame, this transformation is applied on top of the previous state. And that is what the simulation is doing. So this is working perfectly fine. Now let's get rid of these nodes. And I want to be able to control the very first pizza box in the stack with the controller empty from the vehicle. So let's add a object info node. And then I already have the empty in place. So now I can just use the eyedropper tool to select the wiggle control empty. Let's set the position to relative to get it into the right space. And now we can use the transform output to get it into the right place. But we only want that to happen for the very first pizza box in the stack. So let's use a switch node. And for the switch input, we can compare the index to 0 and check that only when the index is equal to 0, we want to set this transform. But now we actually need to apply this information to our stack. Right now we only stack up all the boxes at the very end with our randomization setup. So what I want to do is combine this with the simulation that we're doing. And we're going to do this very similarly to what we've done before. So let's combine the output from the simulation with another accumulate field node. Make sure to set the domain to instance. And then this just as well will accumulate all the transforms throughout the whole stack. And the transformations that we're going to get out of the simulation are just going to be the additional offset that we get from the bounce. So let's combine these two transformations with another multiply matrices node. Let's connect the offset into the first slot and then the stacking into the second. And you can see how the stack already snaps to the control of the empty. This is working because the very first pizza box is getting exactly that transform set from the simulation, and then the accumulate field node will give us this exact transform for all the boxes on top of it as well. The reason why we're using the leading output here, while we were using the trailing output before, is that now for the offset, we want to include the transformation value for each box itself. So here, the offset transformation for the bounce is used for the box itself, plus all the previous ones combined. For the stacking itself, we did not want to consider the height of the box itself, but only the previous ones. So right now with this base setup, the entire stack moves perfectly along with the control empty. But that's not actually what we want. Now that we have the bounce of the empty stored on the very first pizza box, let's try and propagate that through the stack for each frame. So instead of storing nothing as the transformation for the other boxes, we're going to take the information of the previous frame and then use an evaluate@index node to plug that into the false input of the switch. Make sure to set the domain to instance. And then for the index input, we're going to duplicate this index node and subtract 1. And that will, with each frame, pass through the transformation of the box below, all the way through the stack. At this point, we get a little bit of a problem where everything just disappears. But as you take a close look, this is happening over a couple of frames. And everything's just shrinking. The reason for that is that there's a difference in scale between the pizza box object and the controller empty. Here, we don't really care about the scale, we just want things to rotate and offset. So what we can do is do a separate and then a combine of the individual transform components and just leave out the scale. Now the pizza boxes are way too big, but we can just manually scale them down to the size that we need. And if I play this, you can see how now this is working perfectly fine. With each frame, the bounce from the first box is propagated like a wave all the way through the stack. If I increase the size of the stack, we need to go back to the very first frame to actually see the effect. But you can see how this effect is very clearly visible. To actually change the height of the stack in real time, we need to change the setup a little bit. Instead of just passing in the geometry through the simulation input and then using that later on, which will store the very first frame that the simulation is running, we need to pass it in differently. So let's add a sample index node into the simulation. Set this to matrix and then instance. And instead of directly using the matrix input from the simulation, we're going to sample it exactly from the same index, and then connect the outside of the simulation. This means that each frame we update the new stack with the changed height, which can have a different amount of instances, and then sample the simulated data from the previous frame. So now if I play back the simulation, you can see how we can dynamically change the height of the stack, and the simulation adapts to that. And those are the most important aspects of this demo setup done. There are a few additional things that I'm doing in the demo file, so if you are interested, you can check those out. But I hope this should give you a good kickstart to understand what you're looking at. And that covers most of what you need to know to get started using the matrix socket in Blender 4.2. Make sure to also check out the video about the new things in Node Tools to learn another application of using the matrix socket.